So we can start our lesson, today's lecture number 8, theme 8, accuracy of the form and relationship of surfaces and surface roughness. Please write down this theme to your notes and write down the plan. 8.1 deviation of the shape and deviation of relative position of surfaces, and 8.2 standardization and designation of surface roughness. So we start item 8.1, deviation of the shape and deviation of relative position of surfaces. The principle of adjacent straight surfaces and profiles is put in the basis of the normalization and reference system for deviations in the shape and arrangement of surfaces. An adjacent straight line plane is a straight line plane, like in this figure, this line or this plane. Straight line or plane is a straight line or plane that touches the real surface and is located outside the material of the part, so that the deviation from it to the most distant point of the real surface within the normalized area has a minimum value. This distance, delta, minimum, it's maximum distance between this line and real surface. The adjacent circle or cylinder is a circle of minimum diameter described around the real profile of the outer surface. Look at this figure. You can see the real profile, and you can see the circle around the real profile. This circle described around the real profile of the outer surface of rotation of the maximum diameter, which is increased in the real profile of the inner surface of rotation. From deviation is a form deviation is a deviation of the shape of the real surface from the shape of the nominal surface. Please write down to your notes this part of the slide. So, form deviation is the deviation of the shape of the real surface from the shape of the nominal surface. The nominal surface is understood as an ideal surface, the shape of which is specified by the drawing or technical specifications. The value of quantifying the shape deviation is the greatest distance along the normal form, the points of the real surface or profile to the nearby surface. The largest allowable value of the form deviation is called the form tolerance. Write down to your notes this part of the slide too. And we continue. Next slide. Form deviations can be complex and partial. For cylindrical surfaces, the deviation from cylindricity is complex, characterizing the greatest distance from the points of the real surface to adjacent cylinder. For cylindrical surfaces, shape deviations is transverse and longitudinal sections are considered. In cross section, like in this, like in previous slide, in cross sections. In cross section, this is the deviation from the circle, the greatest distance from the point of the real surface to the adjacent circle. Particular types of deviation from the circle are ovality and cutting. In figure 8.2, you can see deviation of the shape of cylindrical surfaces in the longitudinal section. A is taper, H barrel-shaped, and I saddle. Deviation is calculated by this formula. D maximum minus D minimum divided by 2. D maximum, it's maximum diameter of the real surface. D minimum, it's the minimum diameter of the real surface, and we can calculate deviation of the shape of cylindrical surface in the longitudinal section. Longitudinal section. And in cross section, we have ovality and cut. Ovality, deviation from the circle when the real section profile of the part is an oval. Real profile of the part is the oval. And the largest D maximum and smallest D minimum, largest D maximum, smallest D minimum diameters are in a mutually perpendicular direction. One direction and second direction, they are mutually perpendicular. Cut deviation from the circle when the real profile is a multifaceted figure. Multifaceted figure, like triangle, like in this picture, in this figure, and we have the delta, is distance between two profiles, real profile and profile of the circle, ideal circle. And delta is calculated by the same formula, d maximum minus d minimum, and divide by 2. In the longitudinal section, a complex indicator is the deviation of the profile of the longitudinal section. This deviation is characterized by deviations from the straightness and parallelism of the generators. In figure 8.2, it's 8.3 figure. You can see deviation of the shape of cylindrical surfaces in the longitudinal section. J, taper, H, barrel-shaped, and I, saddle. Particular types of deviation of the profile of the longitudinal section are conical, barrel-shaped, and saddle-shaped. Conical, barrel-shaped, and saddle-shaped. It's particular types of deviation of the profile. 3 types. First type are conical, second type barrel-shaped, and third type saddle-shaped. For flat surfaces, the complex indicator is the deviation from the plane, and the partial indicators are concavity and convexity. Figure 8.5. Form deviation. A, it's deviation from straightness. CED, deviation from flatness. A and B, it's deviation from straightness, and CD, deviation from flatness. An indicator of the deviation of the cross-sectional profile of flat surfaces is the deviation from straightness. The deviation of the location of the surfaces is the deviation of the actual location of the surface axis to plane of symmetry from the nominal location. To assess the accuracy of the location of surfaces, bases are usually assigned the base of the surface, axis point or plane of symmetry, relative to which the location tolerances are set. Total deviations of the shape and location of surfaces. The radial runout of the surface or revolution is determined by the total deviation from the cylindrical surface and the deviation from coaxiality relative to the base axis. And runout is determined by the total deviation of the end surface from the plane and the deviation of this surface from perpendicularity relative to the base axis. Graphic sign of shape tolerances and the location of surfaces, their numerical values and designation of the bases are placed in a frame divided into 2 or 3 parts. In the first place, the tolerance sign. In the second, the numerical value of the tolerance, and in the third, the designation of the base. Base axes and surfaces are marked on the drawings of parts in accordance with ISO with an equilateral shaded triangle connected to a frame in which the designation of the base is written in capital letters. If the base is an axis or plane of symmetry, then the triangle is placed at the end of the dimensional line of the corresponding size. When assigning a location tolerance for 2 surfaces, use an arrow instead of darkened triangle. The frame is connected to the contour line of the part or extension line. If the tolerance refers to the side surface or profile, then the frame is connected to the contour line or its continuation. In this case, the connecting line should not be a continuation of the dimension line. And now, before we start item 8.2, standardization and designation of surface roughness, we can see some videos about item 8.1, deviation of the shape and deviation of relative position of surfaces. And of course, about surface roughness. Video number 1.
Welcome to academic game tutorial with finish. Differences between surface roughness and surface finish. Although surface roughness and surface finish are frequently used interchangeably and also signify same thing, they are different in several ways.
In this figure, you can see real form of the part. We can see profile of the surface, form of the surface, waviness, and roughness. Roughness height, the value of roughness in micrometers. You can see macro level, it will be waviness in the micro level, micro level, it will be roughness.
Surface roughness refers to the height of macro and micro asperities and irregularities present on a finished surface after machining, while surface finish indicates quality of that surface using various attributes like fine, rough, good, poor, etc. So, let's look into the basic differences between surface roughness and surface finish in a tabular form. Difference number 1. Surface roughness can be measured with the help of suitable instruments, whereas surface finish is not measurable. Value of surface roughness can indirectly indicate level of surface finish. Number 2, surface roughness can be expressed quantitatively using value plus unit. For example, average roughness of a turn surface is 20 micrometers, whereas surface finish can only be expressed qualitatively using attribute. For example, the turn surface is rough. Number 3, there are several formulas available to estimate surface roughness of a machine surface, whereas no such formula is available to directly estimate surface finish. And difference number 4, roughness always has an absolute value. This is independent of requirement or human perception, whereas attributes used to express surface finish depend greatly on the requirement and human perception. 2 micrometers surface roughness can be termed as good finish when roughness of 10 micrometers is tolerable, or poor finish when mirror finish of roughness 100 nanometers is desired.
Video number 2. Circularity. The tolerance zone.
Hello, everyone. Could be more of a act. What you see on the screen here is our GD&T symbols wall chart, often referred to as the cheat sheet. So up in the top section of this, the green section, this is all of our form controls. Circularity is located up here. So makes great for quick reference. It does show for circularity what the tolerance zone looks like here. And it is 2 concentric circles. Right below here, circularity, what it is how much does the form of a part adhere to a perfectly circular shape. Remember, it's 2-dimensional. So on this one, you're checking how circular a cylinder or sphere is for a given 2D cross-section. Down at the bottom, and again, these are just real quick references, make sure everybody remembers this stuff. For ASME, these symbols that I have shown are always at RFS. That's good to know because it means that we don't have any MMC modifier or LMC modifier involved with this. So keeps our numbers a little bit easier to understand. So if you haven't downloaded this, at the end of this, I'm going to show the link there for downloading the free wall charts. Circularity. So diameter versus circularity. On here, I'm going to show you what it is based off of rule number 1. So there is no circularity called out on here, but we do have a size dimension down here in the lower left-hand corner of this little drawing example that we use for circularity in our course. The size or the diameter is 20 millimeters, plus or minus 0.5. And this does establish a maximum material condition of 20.5. So going back up here to the top, it states rule number 1, which is the envelope principle. Again, some of you may refer to that as Taylor's principle, especially those of you involved with any kind of fixturing and gauging. So it states rule number 1, and the local size measurements need to be met for any given diameter to be in specification. This allows for an indirect circularity control based on the limits of size. So again, I know that we have covered all of this before with you, but I want to show you something here. So if we pull this up, this is showing that MMC size, right? That is that envelope. And now it's 2-dimensional, right? But the actual gauge, the go gauge that we would design for this would be 3-dimensional. We wouldn't be trying to check it on a 2-dimensional basis. But this control for circularity is technically 2-dimensional. Now, that size dimension down there, that 20 plus or minus 0.5, that does have straightness and cylindricity involved with that too. So when it comes to these form controls that are built in by rule number 1, it's whatever is applicable, meaning what does the geometry look like? If it was a flat surface, well, then it would be straightness and flatness. Flatness being the 3-dimensional, it would wind up being flatness and indirectly controlling straightness. But for this topic, we're really just looking at the tolerance zone of circularity and want to show you something that I know me personally, I've taken this for granted. So that 20.5 sitting there, that is our envelope, right? Everybody understands that part of it. No surface element, even a single surface element, can go beyond that boundary of maximum material condition, the envelope. So that's represented by the red circle on here. And then now they're showing the 19.5. Well, we all understand and know that that is the least material condition, right? Going back over here to the lower left-hand corner, 20 millimeters plus or minus 0.5. Well, if we subtract 0.5 from that, we get 19.5. The next one up is what we took for granted, or me personally. So this green circle that's on the inside here, notice how it's tangent to all of these low points or these valleys on the surface. Now, LMC is still maintained, right? 19.5. But note here that the valley here is coming tangent, and then they're measuring straight across. So that's LMC, but this circle right here that they're showing is not LMC. In our classes, when I'm teaching circularity, I will stop and ask if everybody knows what this green circle's diameter is. Everyone always says 19.5. It's not 19.5, as you can see right here. The circularity tolerance is 1 millimeter, right? That's rule number 1 over here. And remember that what they're showing right here, the distance between the two circles, that is the definition of the tolerance zone for circularity. We have 2 concentric circles, concentric by the English definition. And then that distance right here, it's not diametric, right? It's the distance right here. And when we don't see circularity on the drawing, it's this right here, this total size tolerance. Now, that produces a diameter inside of here that is 18.5, right? 20.5 on maximum material condition out here on the outside diameter. But anywhere around here, this surface can dip all the way down to that 1 millimeter distance. Well, that is the 18.5 in here. Notice that 19.5 is tangent here to the inner circle, but then going out tangent to the maximum material condition. Now, what this is showing is that surface on any given element, it is allowed to move within this tolerance zone. And again, that tolerance zone there is not LMC. That's a different one. LMC is the measurement, right? We always talk about when it comes to LMC like this on an external feature, and same rule applies for internal. We have a maximum material condition boundary, right? We can set a gauge diameter for that. And in our course, we tell you measure the LMC. And those are our 2-point measurements that must pass, right? Nothing can be smaller than LMC, which is what they're showing right here. Nothing can be smaller than LMC for this, no 2-point measurement. And then nothing can be greater than maximum material condition with this external feature, meaning nothing can go beyond the envelope of 20.5. So keep in mind when you're dealing with circularity, and this right here is actually a good thing for designers to look at, in that when you put a sloppy tolerance on a diameter, like we've intentionally done here, obviously this is all exaggerated for effect, but this does happen from time to time where you recognize that you can handle a lot of size tolerance. And maybe you're putting a position tolerance on it. Well, remember that whenever we get into adding our geometric tolerances like position, if we give a sloppy tolerance to the diameter, position is not going to come back and help you as far as what the scenario we're looking at right here, this lobing. That is from the form. That's going to be controlled by size. And that might indicate that you need to go back and add circularity as a refinement of rule number 1 to this to make sure that it can't get as bad as what we're showing here. Because it's 1 millimeter for some of you, that may be a reasonable tolerance. For a lot of others, that would be considered a very sloppy size tolerance on there. But remember that this can happen. This green circle is going to move based off, if you were to do a refinement of circularity, it's going to move closer to that maximum material condition size. And the more tight control you need on your form. Obviously, the tighter the refinement of rule number 1 is going to be with the use of circularity. One other thing to point out here is this is tangent out here to MMC. If we go directly across, this is tangent to this inner circle, the inner tolerance circle for circularity. Now, the 2-point measurement across here would have to be 19.5, right? Nothing can be above or outside of the MMC. Nothing can be below or smaller than the LMC, in this instance, since it's external. So keep that in mind. Again, we just wanted to make this quick video to show you the actual tolerance zone here and explain what that inner green circle is, because it seems like more often than not, as everyone goes through circularity, that they're not paying attention or understanding what that inner circle is.
So, the next video, it's introduction to surface texture specification and verification.
Complex specifications. The surface of a cylinder bore must have crossed grooves to allow sufficient lubrication of the moving piston to avoid engine tightening. But these grooves must not be too deep, or they may potentially increase compression losses or lead to excessive consumption in fuel and oil. The cylinder head gasket ensures sealing both by its form and its chemical composition, but also by its surface texture, and by the surface texture of the opposite sides which are in contact with the cylinder head and the engine block. Injectors are crucial parts that ensure the performance of the engine and its ability to meet modern emission standards. Most internal surfaces around of the injection nozzle are specified precisely in surface texture. The pinions of a gearbox are specified in roughness and waviness to ensure their performance in the greatest silence for driver and passengers' comfort. Many other components of a vehicle also have their surface texture specified and controlled. The grained plastic of the dashboard, the connector contacts of wiring harnesses, the metal inserts and the buttons of the dashboard, the car body at different stages of preparation such as cataphoresis, primer, and the different layers of paint and varnish. Outside the mechanical and automotive industry, many objects of everyday life are also controlled for functional reasons or aspect. The metal shell of a smartphone must have a soft touch that ensures a good grip, but should not to be marked with fingerprints. It should not get dirty too easily and must also offer a luxurious look. Its surface texture is controlled by many complex specifications. The front glass protects the screen, but it is also a tactile area which must accurately respond to the fingers of the user. Grained plastic of a laptop case or of the keyboard keys provide comfort of touch and effectiveness in operation. Connectors must ensure good electrical contact and sufficient clamping during insertion and withdrawal. One could multiply examples endlessly. All these products and manufactured objects we use every day are controlled by the industries from their design to their production to ensure that they provide the desired function with maximum efficiency. The function of a surface corresponds to the designer's intent. A component should adhere to another, or on the contrary, ensure lubrication when sliding on another surface, or enable effective tightening. The designer of the part specifies dimensions but also its surface texture to ensure that the function will be realized correctly during manufacturing. Many parts today are manufactured by subcontractors, often in distant countries, and accurate specifications reconcile requirements that should be respected. This is called functional specification, defined in GPS standards of geometric product specifications and verifications. These specifications are given on drawings. They must then be verified to assess compliance of the component. Regarding surface texture, the ISO 1302 standard describes a visual specifications language that designers must use on mechanical drawings. An indication of surface texture is done through the root symbol, associated with indications that provide the parameters to be controlled and their limits. Indications of surface texture are part of the tolerancing of a workpiece, as are indications of size and position. This standard will soon be replaced by ISO 21920-1. The metrologist responsible for verifying a workpiece on a production line will sample some parts to measure them. He or she will rely on specifications written on the drawing and will use a profilometer or any other suitable means to measure profiles, or sometimes surfaces, and then calculate the surface texture parameters that are specified to finally compare their value to the tolerance limits. When checking surface texture of a workpiece, a measurement is made at a location indicated on the drawing, generally a limited portion considered as representative of the surface to check. For example, a profile is measured on a portion of a drive shaft. What is measured, materialized by the profile, is actually composed of several surface texture components that are treated differently in surface texture analysis. The nominal form is the geometric shape of workpiece. This is usually a straight line in the case of a flat part or a circular arc in the case of a cylindrical part, superimposed on the surface texture. This nominal form is deleted by calculation, since we are interested here only by surface texture, not geometric dimensions. The form deviation is due to inaccuracies in the production of the theoretical form during machining. A workpiece that is supposed to be cylindrical is in fact slightly oval because of, for example, the biasing of the tool axis. This form deviation is also removed by filtration. The waviness and roughness are the main components of surface texture, and these components are the main objects of tolerances in surface texture specifications. Waviness is made of longer wavelength components than roughness. They are separated in practice using a filter which can be adjusted by a cutoff lambda c that depends on the application. Roughness is the most important for almost all functions. Each machining process leaves a signature on the surface which results in specific roughness and oriented grooves. Waviness is important especially when surfaces are in contact with each other, for clamping functions, sealing or sliding. Micro roughness contains the smallest wavelengths. It comes mostly from instrumental or environmental noise. In most applications, this micro roughness is removed by a low-pass filtering. We see here how the elements of finer texture find themselves in the roughness and the longest in the waviness. This separation concerns lateral wavelengths in the horizontal plane, not the amplitude of the texture. The sum of waviness and roughness is the primary surface or the primary profile. It is possible to tolerance one or the other of these components with roughness, waviness, or primary parameters. For example, a parameter RQ will be calculated on the roughness profile, WT parameter will be calculated on the waviness profile. The mechanical part is first imagined by the designer on his CAD software. On the drawing, he adds dimensional tolerances and surface texture tolerances. But before getting a profile on which the metrologist can calculate parameters, he must go through a conceptual stage which involves the theoretical profile on which tolerances are applied. The nominal profile is the theoretical profile, mentally constructed by the designer using a partition operation on the geometrical part. The partition is realized here by taking an intersection plane vertically through the volume of the workpiece and isolating the workpiece top, resulting in a rectilinear profile. This profile is then qualified with a surface texture specification, for example using the parameter RQ and the upper limit of 0.7 microns. The nominal profile is a theoretical profile imagined on the drawing. This is generally a line or an arc, or in more complex cases a spline shape. The reality on the workpiece is unknown to the user, because one can only produce an abstraction of reality. The user can only know what goes out from the measuring instrument. Nowadays, it is a digital representation, sampled along x, in successive points, spaced by a constant spacing delta x expressed in micrometers, and digitized in z, using integers, spaced by the value of a digit delta z expressed in nanometers. In the case of a 3D measurement using an optical profilometer, an image of heights is obtained where z is a function of x and y. It is common to represent the data using an anamorphosis, which amplifies the z-axis much more strongly than the x-axis, to better see changes in heights. In reality, the surface is almost flat and drawing the profile to scale would show us only a straight line without details. Valleys and peaks visible on a profile are therefore greatly exaggerated compared to reality. In the case of a surface, it is also amplified on the z-axis, but heights are also encoded using a color palette that separate the local variations of height. Again, changes in the topography are greatly amplified, and a surface drawn to scale would appear completely flat and smooth. Finally, a question asked by many users: should we measure the surface in 2D or 3D? Should we calculate parameters on a profile measured along a straight line or on a surface measured on a rectangular portion? If surface texture metrology has long been exclusively profilometric, it is partly because of technological limitations of measuring instruments, but also because industrial surfaces were then simple enough to be reliably analyzed in 2D. But over the last 20 years, this is less true, and we can say that we are witnessing a paradigm shift in 3 parts. Firstly, surface texture measuring instruments evolved from profiles to surfaces. Nature is 3-dimensional, and some functions can be analyzed more reliably using surface parameters. It is said that one gets better functional correlations. Secondly, technology moved from contact to optical. This allows faster measurements and makes it possible to measure fragile materials without damaging them. Thirdly, industrial surfaces nowadays are often structured or textured to imprint a special texture that performs the desired function. For example, hydrophobic surfaces are often equipped with microscale geometrical structures such as pillars or pyramids to prevent droplets from adhering. They require new analysis tools and require aerial measurements. These 3 reasons explain why surface metrology has changed so much in recent years and that new analytical tools and new measuring instruments have appeared. Discover more videos and resources on our surface metrology.
So now we start the item 8.2, standardization and designation of surface roughness. Surface roughness, according to ISO, is a set of surface irregularities with relatively small steps within the base length. Base length, small l, base length. This distance, this dimension. The length of the baseline, which is used to highlight the irregularities that characterize the surface roughness. This line, its base length. Surface roughness, regardless of the material and method of manufacture, obtaining the surface can be quantified by one or more parameters, which include: first parameter, R suffix A, RA. Arithmetic mean deviation of the profile, R suffix Z. Height of profile irregularities at 10 points, 5 protrusions and 5 depressions. R suffix maximum, the greatest height of inequalities. S suffix M, the average step of profile inequalities. S, average step of inequalities on the vertices. T suffix P, relative reference length of the profile. Please write down to your notes this parameter, RA, RZ, R maximum, SM, S, and T suffix P. And now we can see next, we can look next video about roughness. Amplitude, profile parameters.
The main profile parameters are defined in the ISO 4287 standard that was published in 1996. This presentation will introduce the amplitude parameters defined in this standard. A measured profile is a series of height values in function of the lateral position. Heights are referenced by convention from the mean line, which is calculated as the mean value of all heights. This mean value is set as 0. Heights are positive above the mean line and negative below. A portion of the profile above the mean line between two zero crossings is called a profile peak. A portion below the mean line between two zero crossings is called a profile valley. They can be combined in a profile element as a peak followed by a valley or a valley followed by a peak. One can measure the highest extension of the profile above the mean line. This height defines the parameter pp, called the maximum profile height deviation. The parameter name starts with a capital letter P, as we are on a primary profile. Its suffix is a small p to designate peaks. Similarly, the deepest extension below the mean line defines parameter PV, called maximum profile valley depth. The value of PV is positive because it is counted as a depth downward from the mean line. The suffix V in PV stands for valleys. Then, the vertical distance between the highest peak and the deepest valley defines parameter PZ and is called maximum height of the profile. This parameter is a first evaluation of the amplitude of texture. However, it is very sensitive to outliers, extreme peaks or valleys that are not significant in terms of function of the surface. The PZ parameter makes it possible to discriminate two surfaces by comparing their maximum heights. Here, we can say that the above profile is rougher than the profile below by just comparing their respective PZ values. But these values do not tell anything about the texture morphology of the surface. How heights are spread between the min and max values? That we don't know. Here, the two profiles have the exact same roughness amplitude. But if you had to walk barefoot on one of these surfaces, I bet you would prefer the surface above. Roughness amplitude alone is not enough to qualify the functional characteristics of the surface. In practice, parameters are usually calculated on a filtered profile. The filtration operation consists of calculating a profile that contains the longest wavelengths longer than a defined cutoff value. Such a profile is called the waviness. It loosely follows the main long-term variations of the profile without going into each irregularity. The Gaussian filter, here with a cutoff of 2.5 mm, being subject to end effects, the filtered profile is cut on each edge by a length equal to half a cutoff or sometimes one cutoff. The resulting length is called the evaluation length. The roughness profile is calculated by subtracting the waviness profile from the primary profile. It is therefore also shorter by half a cutoff at each end. ISO 4288 specifies that the roughness profile is decomposed into small portions, called sampling lengths, that have a length equal to the cutoff value. Parameters are calculated on each sampling length and are combined in an average value, which is normally less sensitive to noise and outliers. The average helped originally to stabilize profilometer results when used in a noisy environment, such as a production line in a factory. By default, 5 sampling lengths are used, but this number can be adapted in the specification, depending on the application. Each parameter is calculated on 5 sampling lengths, which leads to 5 estimator values. The final parameter value is calculated as the average of the estimator values. Some standards do not use sampling lengths, such as the American Standard ASME V46.1, and calculate the parameter directly on the evaluation length. In the forthcoming new ISO 21920 standard, most profile parameters are also defined in the evaluation length, except for maximum parameters RP, RV, and RZ. Another parameter, RT, or the total height of the profile, can be defined. It is calculated as the sum of the highest RP estimator and the highest RV estimator. RZ is therefore smaller than or equal to RT. On the primary profile, PT equals PZ as there is no sampling length and only one value of each parameter is calculated. So, we have 4 parameters that are applied on 3 profiles: primary, roughness, and waviness, which makes 12 parameters in total. We can add 4 more parameters: RA, RQ, RSK, and RKU, also considered as amplitude parameters. PA and PQ are both calculated from a mean of all point heights on the primary profile. In case of a roughness profile, RA and RQ are calculated on each sampling length, then averaged. They are averages of averages. PA uses an arithmetic mean of the absolute values of heights. PQ is the root mean square of all heights. It is therefore the standard deviation of the height distribution. These two parameters are an evaluation of the mean roughness height that is not affected by extreme points. RA is probably the most well-known parameter and the most used in specifications. It does not mean that it is the most useful or meaningful, far from that. But it is usually the only one known by designers, and often the only parameter taught to students. Using RQ instead of RA would provide similar results but with a physical meaning. RQ, as the standard deviation, or in the variance form, is found in several tribology equations. PSK and also RSK and WSK is a parameter that qualifies the symmetry or asymmetry of the height distribution. It provides useful and important information on the texture morphology. If its value is significantly negative, it means that the surface has a top plateau with deep grooves or pores. On the contrary, if its value is significantly positive, the surface has a flat bulk with high peaks as if particles are deposited on a plane. This parameter would help differentiate the two profiles we've seen previously with the same PZ value. PKU qualifies the dispersion of the height distribution, also called kurtosis, between the min and max values. If its value is significantly larger than 3, then the distribution is narrow with a few extreme points above and below. Most points are concentrated around the mean value. A small value of PKU means that heights are spread more or less regularly between the min and max values. It is another way to describe the texture morphology. However, skewness and kurtosis are pretty sensitive to the presence of extreme points such as outliers, so they should be used carefully. To finish this presentation, let's examine some practical examples. Here, a profile measured in a cylinder bore of a car engine. The fine mean roughness RA equals 0.5 micrometers is to be compared with the large amplitude RT equals 11 micrometers, due to deep grooves that are produced by honing on the surface to ensure lubrication. The skewness parameter RSK is negative and it confirms the presence of scratches below the main surface. The high value of kurtosis RKU indicates that most of the texture is concentrated around the mean height, which is high and close to the top of the surface. Another example, measured on a steel sheet. The texture is well centered around the mean height without extreme points. It is verified with a small value of RSK and a value of RKU smaller than 3. Last example, measured on a ground surface. The distribution shows a nice Gaussian shape, slightly shifted towards the top because of a few deep grooves. Thus, the value of RSK, which is slightly negative, and a large value for RKU. The mean value, RA, is very small compared to the peak to valley RT. All these parameters can be used in specification. Discover more videos and resources on
So we continue. Next slide. The most complete information about the surface of the part gives the parameter RA. So it is the main of the Hague parameters of roughness. The relative support length of the profile TP characterizes the actual support area on which the wear resistance of movable joints and the strength of press fits largely depend. Clean surfaces with low roughness increase the strength and corrosion resistance of parts, reduce actuation friction in mating movable joints. However, this significantly increases the cost of machining parts. Therefore, the choice of roughness parameters should be economically justified. There is no direct relationship between dimensional accuracy qualifications and surface roughness parameters. But high dimensional accuracy with significant surface roughness is not allowed, since the height of the irregularities can be commensurate with the dimensional tolerance. The surfaces of parts intended for connections according to standard fits must have a roughness parameter RA of from 0.2 to 3.2 microns or micrometers. According to ISO, the roughness is indicated on the drawing for all surfaces of the details, which are performed according to this drawing. The structure of the surface roughness designation is shown in figure 9.4. 9.4a. In the designation of surface roughness, the type of processing of which the designer does not set, use the sign shown in figure 9.4b. If the surface roughness is formed by removing a layer of material, for example, milling, grinding, etc., use the sign shown in figure 9.4c. If the surface roughness is formed without removing the layer of material, like casting, stamping, etc., use the sign shown in figure 9.4d. When denoting two or more parameters of surface roughness, the values of the parameters are written from top to bottom in the following order. The height of the profile irregularities, the step of the profile irregularities, the relative reference length of the profile. And in this slide, you can see types of directions of inequalities and symbols in the drawings. Parallel, perpendicular, cross, random, round-shaped, and radial. We use these symbols. Now we have the time, so we can look video number 5, surface finish symbols explained.
Surface finish symbols explained. This is a little bit lengthy of a video. It's approximately 18 minutes. All of the information that you're going to need to write your CFQ that pertains to surface finish is contained within this video. Please take a moment to like and subscribe. It's free and it'll help me out. If you got this symbol on a drawing, would you know what it means? Well, by the end of this video, you absolutely will know what it means. And I will go through this step by step at the end of the video. Okay, let's get started right now. Warning, viewer discretion is advised. This video is made for apprentices, a lot more difficult than what it is, but it's just the distance that we're measuring over. And later on in this video, when I do a demo using the surface roughness tester, it's the amount that the probe travels in and out. Flaw is an irregularity that occurs in a surface due to cracks, blowholes, ridges, scratches. Basically anything that's not in the machining pattern. There is no finish symbols for flaws. A special note should be included on the drawing where no flaws are permitted. Typical ways of obtaining surface roughness measurements is RA, RQ, and RZ. And here's a brief explanation of each. RA is probably the most popular we're going to use. RA is the roughness height, I'm going to butcher this one, arithmetical average. So basically what happens if you take a look at A, B, C, D, E, all these lines have heights or distances. So basically what happens is you add them all up. In this case, if you take a look, it equals 108. So you take 108 and there's 18 spots. So you take the average of them and it's 6. So that's how we calculate the RA. And in this case, with these measurements, the RA would be 6. To help clarify things, RA, RQ, and RZ is just a setting that you're going to be using on the surface roughness tester, and it will do the equation for you. RQ is the root mean square, so roughness height. Just like on the RA, we have 18 lengths. So what we're going to do is we're going to square each length, and then when we total them up, we're going to get the square root from it. So in this case, RA for the same measurement was 6, RQ is 6.4. RZ is the measurement of the 5 largest peaks compared to the 5 lowest valleys over your sample length. Material removal symbols. Identical surface texture all over. This is one of the newest surface texture symbols, and you probably don't have it in your textbook. But that little circle around the bent elbow means all over. Surface may be produced by any method. When this symbol is by itself without any accompanying symbol like a lay symbol, it can be produced by any method, meaning any type of machining. Material removal required. This symbol is usually accompanied by other symbols such as lay. Material removal prohibited. There are multiple reasons why they use this symbol, but one of the more popular ones is that surface is a datum for internal reference dimension. Basic surface texture symbols. Roughness average value. This can be stated in microinches or micrometers or roughness grade. Using the visual comparator, you can see on the top, which is microinches, and on the bottom, which is micrometers. Minimum and maximum roughness average value. This can be stated in microinches, micrometers, or roughness grade as well. By using the visual comparator gauge, if you take a look, the red would be the minimum and the blue would be the maximum roughness. So in other words, as long as you're between these two finishes, your part would be approved. Machining allowance can be stated in inches or millimeters. So this means that they left material on this surface to be removed, usually on castings or on material that have to have a certain amount removed off to prevent warpage, such as cold rolled steel. Maximum wave height can be stated in inches or millimeters. Basically, it is the height of the wave between the peak and the valley. Maximum wave spacing can be measured in inches or millimeters. It comes after maximum wave height. And what it is the measurement of the wave highest peak to the next highest peak, roughness sampling length. Basically, this is the length that you set your surface roughness tester up to measure across. The minimum length, if not stated, will be 30 thousandths of an inch. Lay symbol, the direction of the predominant surface pattern. Lay symbol perpendicular. Lay perpendicular to the line representing the surface to which the symbol is applied. Lay symbol parallel. Lay parallel to the line representing the surface to which the symbol is applied. Lay symbol radial. Lay approximately radial relative to the center of the surface to which the symbol is applied. A lot of older tradesmen will refer to this as a Blanchard ground symbol. Lay symbol angle. Cross in two slant directions relative to a plane of projection of the view in which the symbol is used. Basically, it looks like the cross section of a honed cylinder. Lay symbol multi-direction. An example of this finish would be, let's say, the bottom of a pocket that was machined by an end mill. Bunch of cross swirls, lay symbol, non-directional. This is usually produced by an EDM machine or a sandblaster. Lay symbol circular, approximately circular relative to the center of the surface to which the symbol is applied. This symbol surface is most commonly associated with facing on a lathe. Conversion charts. Take a look at this conversion chart. An RA in microinches of 8 is equivalent to an RA in micrometers of 0.2 and a roughness grade of 4. Surface roughness comparison chart. This can be a little bit difficult to explain, so please bear with me for a few. Sometimes an engineer on a drawing will not put the actual finish that they want. They will turn around, they will say they will require a mill finish. So a mill finish in micro inches is a standard between 250 and 32. So in the yellow. Now the possible parameters is 1000 all the way down to 8. But the acceptable parameters is 250 to 32. So therefore, if an engineer puts mill finish required, he wants a milled finish with a finish variable between 250 and 32 microinches. Visual surface finish comparator. Let's talk about the visual surface roughness comparator. And that's what we have right here. This guy's an awesome visual tool or visual reference for apprentices because it allows them to be able to see right away what type of finish they're getting while they're machining, which is kind of cool. These are not to be touched. Everyone wants to touch them. Oh, I'm running my fingernail up and down them. You're not going to get a super true reading by running your fingernail up and down because they have a bit of a coating on them. Although this guy's nickel, made out of nickel because it's a nickel plated process, how they actually make these. This visual comparator here, if you look really closely right here, there's actually a hair stuck inside of this sample. How I know this is because I ran the surface roughness tester over top and I wasn't getting an accurate reading for what the actual specimen was saying. Now that doesn't mean that it's out, it just means that there's a slight coating on top of it to protect it. But the visualization works great for these guys. Some of the tools that we use to check, you can use a microscope. A microscope's good for a couple of different reasons because you can project it onto a large screen, which works great. And you can also record the image that you have. If you're in a hurry, an eye loop works great. You can also pick up a pair of these funky glasses. They work great. You can use different focuses and they have their own light source. And you also have the good old-fashioned trusty magnifying glass with lights. I like using this one myself because it's just a little bit easier. So let's take a look at a specimen here. So I turn around and I have a block that's been ground. So I want to see what this actually is. So what I would do is I would hold my piece up against here. I would go down to the ground symbol here. And I would look at it and I would say, I only have two options for ground image or ground surfaces here. I got a 6 and I got a 16. Or sorry, I got an 8 and a 16. Neither of them are as fine as what I have ground on here. So it's going to be less than an 8. So let's turn around and use this visual comparator here. And if I look here, I have a 3 and a 2 and a 4. So I got 7, 6, 5, 4, 3, 2. And I take a look here. We go this way here. And I would almost say between the 4 and the 3. And it's so close it could even be a 2. So I'm going to say between this range right in here. So how do I know what it actually is for sure? Because this is only a visual reference. It's a reference tool. So what I would do is I would take this guy here, set it on here, go start. You see this guy moving inward, then it's going to move outward. 3, 4, 3, 7. Let's look at our conversion chart. 3.7 converts over to a roughness grade of 3. And that looks basically what we have, a number 3 roughness grade. Okay, let's try another sample. Okay, so what we have here is the inside of a hard drive. This is a hard drive disk. Let's give it a try and see what we have here for a visual comparator. So we go through and we find our grinding here. We got 8 on the grind. So if we take a look, we can see clearly that this finish is much greater than this finish here. And then they only get rougher up to that point. So it's better than an 8. So let's take a look at our other chart here. Put this down here. I'm going to say it's better than a 2 as well. So let's measure it and see what it actually comes out to be. Point 4. So basically this finishes off the chart. It's 0.4 and the closest in micro inches is 1. I did a couple off-screen tests and an L2 lap is pretty much the same as what we have. Profilometer or surface roughness tester. So why do I keep calling this a surface roughness tester? Because that's what Michitoyo calls it. This also comes with a precision reference specimen. If you looked at this, we used this earlier today when we calibrated the machine. For extra references and zeroing and changing the different parameters, we use these buttons here. When we flip it over, if we push backwards, this guy will be released. And we can also unplug this. Now you can mount this to a surface gauge or any other type of piece of equipment. Then use this extension cord to go from here back into the unit. So 119.7, and this guy's supposed to be 120. It's 0.3 off. When you have one of these electronic units, it's really easy to switch between RA, RZ, and RQ just by switching the parameters. Surface roughness tester, skidded versus probe. But what I want to talk more about is the stylus on the end here. If you take a look, you see that there's a tiny little needle sticking out the end there. That tiny little needle is actually what feeds back information into the system. But this is called a skidded type probe because it actually rides on the bump that's here. This can only check flat surfaces. It can't really check tapered surfaces or round surfaces. Now, if you have just the individual stylus sticking out, a non-skidded type, what happens is you can check round surfaces, tapers, and a few other things. But with this style, you're limited to only checking flat workpieces. Surface roughness tester setup. It is important to be perpendicular when you're setting this up. If not, you'll get cosine error. And if you're unsure of what cosine error is, check out my YouTube video, Cosine Error Explained. With a skidded probe, it is very important to be parallel to the surface to which you're checking. Not so much with a probe style, but with a skidded, it is extremely important. Checking the surface finish of a circular object. It is not possible to do this with a skidded style. It is possible to do it with a probe, though. Checking the surface finish of a groove. It may not be possible to do this with a skidded stylus due to space restraints compared to a probe. There are many different ways of measuring surface finish, including this optical profiler. There's also lasers. I almost feel silly taking this up because I know that just by going through this, you have an understanding of how to actually answer this question. But let's go through it anyways. Let's work our way from left to right. Let's start with the 60 thousandths of an inch. Position, it means machining allowance. I am required to take 60 thou off of this surface. Next up is 63. In this position, it's RA. My roughness average needs to be 63 or better. Here's what a roughness average of 63 looks like using a roughness comparator. Next up is the 3 thou on the top. The maximum wave height can be 3 thou. So the depth from the peak to the valley can only be 3 thou in depth. Next up is the 5 on the end. The 5 is really 5 thou, and that's the maximum wave spacing. So it's from peak to peak, can only be 5 thou. Next up, it looks like an equal sign on the bottom. That equal sign is the lay symbol for parallel. The machine finish is parallel to the surface that this is applied to. Next up is the 30 thou on the bottom right-hand side. This is the roughness sample length. As shown earlier in this video, you can set the sample length using the surface roughness tester. I'm glad to see that you enjoyed the video. If you want to see other great videos, check out my YouTube channel, Shop in Math. If you have any comments or questions,
Okay, have you a question about roughness? You have the question, so we finished our lesson.
Yeah, okay, teacher.
We continue in Friday in this week. So goodbye. Thank you for your listen, for your attention.
Yeah, thank you so much, teacher, and thank you for your effort. Goodbye, teacher.
Goodbye.